A very warm welcome to all the participants of this online training program on thermal power generation, transmission and distribution technology. Myself, Mrs. Indira, Deputy Director, National Power Training Institute, Durgapur. Today in this session, I am going to discuss with you the working principle of the generator and its basic constructional details. The overview of my presentation goes like this: introduction, types of generators, working principle, parts of a generator, and the conclusion. As we all know, generator is an electromechanical device used to convert mechanical energy into electrical energy. Now, who is giving this mechanical energy? This mechanical energy is obtained from the sources like fossil fuel, nuclear power, hydro power, wind energy, thermal power, which is fed to the prime mover, where this source of energy is converted into mechanical energy, which is fed to the generator, which converts this mechanical energy into electrical energy. This electrical energy that is generated is now called as electricity, which can be used for lighting, heating, rotating electrical machineries, etc. in different locations. There are different types of generators. We can classify them on different modes, but here we restrict ourselves to the types of generators which are used for electrical power. So, the generators may be either AC generator or DC generator depending upon the type of output. DC generators may be again self-excited or separately excited depending upon if a separate excitation is required to generate the voltage, or they are self-capable of getting the necessary flux and ultimately the output voltage. The AC generator may be synchronous generator or asynchronous generator. Asynchronous generators are also called as the induction generator. The synchronous generators are those which run at the same speed. So, we will be restricting ourselves to the synchronous generator that is being used in a thermal power plant. The basic principle of operation of an AC generator or alternator is based upon the Faraday's law of electromagnetic induction. Whenever the magnetic flux linked with a conducting coil changes, an EMF is induced. This EMF is directly proportional to the rate of change of flux linked by the coil. Now, through this demonstration, we can see here that there is a winding. This winding is the field winding. When it is rotating, then a voltage is developed across the terminals of the stator winding. So, the EMF that is induced here, we can see that is equal to minus n d phi by dt. N is the number of turns, and the minus sign is because of the Lenz's law that says that the cause and effect are opposite to each other. Now, in a simple generator which produces an alternating current, the current produced is not very large since the strength of the magnetic field is not very large. The principle of electromagnetic induction may be used to produce a magnetic field of much greater strength. If a conductor is wound around a piece of metal such as iron or steel and current is passed through this conductor, a magnetic field is produced around the assembly. This is called as an electromagnet. The strength of the magnetic field produced is determined by the amount of current passing through the conductor. When a stronger magnetic field passes a winding, more current is produced in the winding. In a generator, the amount of current produced in the winding can thus be controlled by controlling the amount of current passing through the conductor that is causing the magnetic field. So, now we understand that an AC synchronous generator consists of four main components. They are the magnetic field, the armature which holds the windings, the exciter which gives the DC excitation to the field, and the automatic voltage regulator. The exciter provides DC current to the field windings. This in turn creates the necessary flux. This flux, when cuts the nearby stator windings, generates the voltage when there is a relative motion between the two. The regulator then senses this output voltage and controls the exciter current. Synchronous generators are used because they offer precise control of voltage, frequency, the reactive volt amperes that are called as the var, and watts. This control is achieved through the use of voltage regulators and governors. Now, when we are talking of the thermal power generation technology, let us see what is the position of the generator in a thermal power plant. As we can see from this diagram, that water is boiled in a boiler which converts this water into steam. This steam is fed into a turbine. The turbine converts the heat energy of the steam into work, and this mechanical energy of the turbine is now converted into electrical energy in the generator, since the turbine is connected to the generator through the same shaft, and the electrical energy of the generator is transmitted to the external grid system through the transmission line systems. For generation of electrical energy by application of Faraday's law, we have seen that three things are important: the conductor, the magnetic field, and relative motion between the two. In most practical construction of alternators, the armature winding is stationary and field poles are rotating, unlike in case of DC generators where the armature is rotating and the field is stationary. This is because a very high power has to be generated of the order of hundreds of megawatts. To accommodate such high power generation, a very high current has to flow in the armature at a very high voltage. To accommodate such high current to the order of some thousands of amperes, large number of conductors are required, due to which the conductor weight increases, and thus size of the stator is huge. Now, where is the generator located in a thermal power plant? We can see now that the position of the generator comes just after the turbine, because the generator is taking the output from the turbine as its input. So here we can see that this is the turbine end, and this is the turbine end, and this forms the generator. So together it is called as the TG floor. So the generator has turbine on one end, that is the input side, and the exciter, the excitation system on the other side. The control rooms are also located in this floor. The two main parts of a generator now we can say are stator and rotor. The stator constitutes the stator frame, stator core, stator windings, and the terminal bushings. So after discussing about the working principle and the basic parts of a generator, from this diagram we can identify that the outer part is called as the stator and the inner part, this is the rotor. Stator is the stationary part of the generator that embodies the core and the armature winding. It is totally enclosed, gas tight, fabricated structure. It is subjected to magnetic vibrations, so arrangement has to be made to dampen the vibrations. Since it holds lot of conductors for generating a large voltage and a very high current, thus it is the heaviest load in the turbo generator. The stator frame, as we can see, is made of welded steel, single piece construction. It supports the laminated core and the winding. It has radial and axial ribs having adequate strength and rigidity to minimize the core vibrations, and suitably designed to ensure efficient cooling. Guide bars are welded or bolted inside the stator frame, over which the core is assembled. We can also see that the footings are provided to support the stator foundation. From this figure we can understand that a stator frame is a very important part of the stator which gives support to all the internal parts, the stator and the rotor. We can again see here an enlarged view of the stator frame. These are the vents for allowing cooling of the stator, and this is the hollow stator frame inside which the rotor will be inserted, and we can see that the stator slots in which the stator conductors will be placed, and these are the support for the stator which can hold the whole weight of the stator on the ground. The stator core is made of silicon steel with high permeability and low hysteresis and eddy current losses. In order to minimize the eddy current losses of the rotating magnetic flux which interact with the core is built of thin laminations about 0.35 millimeters to 0.5 millimeters. Each lamination layer is made of individual segments. We can see here these are the different segments, the laminations, which will be assembled again to form one complete lamination. Now the stator core is made of cold rolled grain oriented lossless steel. We can see here how each of these lamination segments are assembled in order to form the stator core. Since the generator is very huge in construction, so the stator core cannot be obtained in one single piece. So they have to be assembled with smaller segments. The electrical energy in terms of voltage and current is generated in the stator windings. So the stator windings are three-phase, double-layered, short-corded, bar type windings having two parallel paths. The windings are subjected to thermal as well as mechanical stresses. Hollow conductors are used to provide a path for flow of coolants, because we understand that the stator holds a very large number of conductors, and when a large current flows through these conductors, huge amount of heat is developed, and there should be a mechanism to dissipate this heat into the external, otherwise the efficiency will be reduced and the life of the windings will be reduced. Here we can see the stator windings. These are the stator windings. You can see that they are hollow. So these windings are to be inserted into the stator slots. The length, these are the conductors, and these are the ends which are to be tied up with the core. The bar consists of solid and hollow strands distributed over the entire bar cross section, so that good heat dissipation is ensured at the bar ends. All the solid strands are jointly braced into a connection sleeve, and the hollow strands into a water box from which the cooling water enters and exits via Teflon insulating hoses connected to the annular manifolds. Here we can see that this is the stator, and these are all the windings which are already inserted in the stator slots. These windings, when they are brought to the external, you can see that they are being transposed in order to minimize the losses, and the stator windings consist of two layers. These are the stator slots which are having two layers made of individual bars. Each bar consists of a large number of separately insulated strands to reduce the skin effect losses. Now, the voltage that is generated at the terminals of the stator, they are to be brought to the external through the bushings, through three terminals, by means of the porcelain bushings. The beginning and end of the three-phase windings are brought out from the stator frame through bushings which provide high voltage insulation. The bushings are bolted to the stator frame at the exciter end. Now, after having a detailed understanding about the different parts of the stator, we can see from this cross section that this outermost part, this is the stator frame, and you can see that the next, this one is the stator core and the inner frame. Then we can see that there are some terminal pockets for release of gases, etc. then the stator core, and ultimately this is the end plate. This is the three-dimensional view of a stator. We can see here, these are the annular ribs, then these are the slots for holding the stator windings. This is the end plate which holds all the windings together. This is the core end plate. Then these are the side view of the stator core assembly. Next, coming to the rotor. Types of rotors: rotor shaft, rotor windings, and rotor fans and wedges. Now the rotor, we can see the location here. This is the rotor coming from the one end. This is called as the retaining ring. Then there are cooling fans. Then this is the rotor windings. This is the poles and the cooling fan on the other side, and the rotor shaft. There are mainly two types of rotors which are used in construction of an alternator. They are the salient pole type rotors and the cylindrical pole type rotors. The salient pole type, which means, salient means they are the protruding or the projecting poles. They are generally used for slow speed machines like in the hydroelectric power plants, where the rotor is made up of salient pole type rotor, because the rotor has to move through the water, so the speed of rotation is not much. And from the formula that F is equal to Pn by 120, we see that if the speed of rotation is not much, then the number of poles will be large. So in case of salient pole type of rotors, there will be large number of poles. So they have large diameters and smaller axial length. The poles in this case are made of thick laminated steel sections riveted together and attached to a rotor with the help of joints. The cylindrical rotor, which is generally used in the thermal power plants, they are called as the turbo generators. They are generally used for a very high speed operation. The cylindrical rotor type machine has a uniform length in all directions, giving it a cylindrical shape. So we can see here that the speed of rotation, since it is a synchronous generator, the speed of rotation being fixed, so the number of poles here are only 2, due to which the speed of rotation becomes 3000 rpm. The cylindrical rotor has a number of slots along its outer periphery for hosting the field coils and the poles. We can see here, this is the cylindrical rotor in the thermal power plant. You can see that it is very smooth on the outer surface. In order to minimize the losses due to thermal stresses, heat, mechanical stresses and centrifugal forces during rotation, the rectangular or trapezoidal rotor slots are milled on the rotor surface. We can see on the outer surface, these are the slots to hold the field windings. Rotor windings are made up of copper alloyed with silver about 0.1% concentration, so that coil deformations due to thermal stresses are eliminated. The rectangular cross section copper conductors have ventilating ducts on the two sides. These are the sides, this side and this side, thus providing a channel for hydrogen flow for cooling purpose. Micanite is used for lining the slots as an insulator. Mica is also used as an insulation between the windings of the conductors. Duralumin wedges are used to prevent the lifting of the winding out of the slots during rotation. So, this is the end of the rotor. We can see that the windings are already inserted in the slots, and the ends are together, they are bound by the end plate. Now we can see here, these are the wedges. To protect the winding against the effect of centrifugal forces, the winding is secured in the slots with wedges. These are the wedges. These wedges, they are inserted in these slots after the windings are inserted. The slot wedges are made of copper alloy, because since the wedges are inserted on the top of the windings, we have to keep the conductivity intact. Hence, the wedges are made up of copper, which give a high strength and also good electrical conductivity. Now, once the wedges are inserted on top of the field windings and properly sealed, then even at such a high rotation of 3000 rpm, it is ensured that the field windings do not fly off or break off from the rotor during rotation. Now, since the rotor has a number of slots, rotor windings are inserted in these slots. On top of that, the wedges are also fixed. So, all these windings have to be firmly fixed at the ends, so that they do not get loosened while rotation. So, these centrifugal forces which may be developed during rotation, they are limited and minimized by a single piece of retaining ring, which are made of non-magnetic high strength steel, in order to reduce the stray losses. These retaining rings, they are first heated so that they will expand a little, and then they are inserted on the end of the rotor, and they are shrunk fit on the rotor shaft and held in position by means of a locking ring. We can see the retaining ring here. Now, this retaining ring is fixed here, and once the retaining ring is permanently locked, then we cannot see the conductors at the end of the rotor, and the field conductors are now tightly fixed to the rotor surface. Now, since the field system, that is the rotor, is rotating now. So due to the large magnitude of currents flowing in the stator windings and the effect of the magnetic field through the stator generating the necessary EMF, so there will be a large amount of heat that is developed within the gap between the stator and the rotor surface also. If this heat is not driven away or driven out of the rotors, then it may increase the losses and ultimately the efficiency will reduce. Also, the life of the rotor will reduce. So, there are two fans at both ends of the rotor. The cooling air in generator is circulated by two axial flow fans located on the rotor shaft, one at each end. The blades of the fan have threaded roots for being screwed into the rotor shaft. The blades are drop forged from aluminium alloy. Threaded root fastenings permit angle to be changed. Each blade is secured at its root with a threaded pin. Slip rings. As we understand that slip rings are required to conduct the current to the external circuit. So, the slip rings are provided on the rotor shaft to feed excitation current in field windings. They are made of alloy steel and insulating material, insulated and shrunk fit on rotor shaft. The surface of the slip ring is grooved to provide continuous and reliable contact of the brushes without sparking for better current transfer. Because as we understand that the current which flows through the field winding will produce the necessary flux. This flux, when links with the stator conductors, will develop the EMF. So, the slip rings along with the brushes, they have to be properly in contact so that the transfer of current will be done effectively. We can see here, this is the slip ring assembly in which the slip ring and the brushes are fixed, and there should be proper insulation between the winding surface and the slip rings. Carbon brushes are provided circumferentially on the slip rings to make the electrical connection with the slip ring. As we understand that since the rotor is rotating, the carbon brushes are placed so that there will not be any sparking near the slip rings, which may generate heat and again loss. So the brush gear is made from high precision casting made up of brass. Brushes are spring loaded to maintain the required contact pressure, because since the the field is rotating, the brushes should not come in contact with the rotor, but at the same time they should be so close that the electric current from the field windings can be linked to the external. In case of generators with brushless excitation system, there are no brushes and slip rings. This is the brush gear, we can see here. These are the brushes. Another important part of the turbo generators are the bearings. The bearings hold the generator as a whole firmly, minimizing the vibrations during the rotation and during operation. They are provided, so the turbo generators are provided with pressure lubricated, self-aligning elliptical type bearings to ensure higher mechanical stability and reduced vibration during operation. The bearings are provided with suitable temperature element devices to monitor the bearing metal temperature in operation. We can see this is the front side and this is the side view. The bearing assembly as a whole, the bearings are held in position by means of the oil and the pedestal with proper insulation also. An important part of the generator are the terminal bushings. As we understand that the generator terminal, that is the stator terminals, give us at the output of the terminals we can get the voltage, whether it is single phase or three phase. Now these terminals have to be properly connected and addressed in order to get the voltage. So the stator terminals are connected with the porcelain bushings. These provide proper insulation. So the effective sealing is provided between the terminal bushings and the stator body to avoid leakage of hydrogen. Now this is the terminal bushing. After a brief explanation about the different parts of a generator, now I think it is easy for you to identify the different parts from this block diagram. The outermost part, this is the stator frame. Just below the stator frame, we have made space for the windings. So this is the stator core, which has slots, and the windings are there in the slots. Now the windings are in a coil shaped. So the sides of the coil are the conductors and the ends of the coil, these are the ends. They are called as the end, they are called as the overhang portion of the coil. One side of the coil is the winding inserted from one slot, comes back through another slot to the same side and connected here. So these are the stator winding. This is the rotor which holds the rotor winding and the poles. The rotor is also connected on both sides. Here we can see the rotor fan, then the shaft, the rotor shaft seal, then there's the bearing side, and here we can see these are the terminal bushings. These are the stator windings. All the windings are clubbed together in 3 terminals, because here we are getting the output voltage in 3 phases. So these 3 terminals, through the terminal bushings, the stator terminals are connected to the generator transformer, because the output voltage of the stator windings is not very large. So the 3-phase power generation, it is preferred over a single phase power generation, as it is more efficient, and 3-phase power uses less material for a given capacity, so the costs are significantly reduced. But the question remains that the output voltage of the stator is not very high. It may be of the order of about 25 kV or 30 kV. Our objective is now to direct this generator output to the transmission system so as to transmit to long distances for distribution thereon. Hence, these are the generators which are generating voltage in a thermal power plant. For the 3 phases, these are the 3 terminals which are connected to 3 generator transformers, phase RYB or ABC, which whatever is the nomenclature. These are the 3 phases. So the voltage of the generator output is stepped up to a high level for transmission, and we know that the transmission is done at a very high voltage in order to minimize the losses and also to reduce the I square R loss particularly. So the generator transformer which is connected or which is housed just close to the generator terminals takes in the generator output voltage as its input, steps up this voltage to a higher level, and the output of the generator transformer is now a magnified voltage. This output of the generator transformer is now connected into the switch yard through the bus bars. Now the switch yard holds the various components. Ultimately, the output from the switch yard is connected to the transmission line towers through 3 bus bars, and thus the voltage that is generated in a thermal power plant in the stator is now transmitted to the external transmission line system, and Now we can see here the transmission line level voltages, they may be 132 kV, 220 kV, 400 kV, 750 kV, 1000 kV, depending upon the level of the generation that is being done in the power plant. So this is called as the primary transmission voltages. In this level there are no tappings. These are only for transmission for up to a long distances. On the receiving end, these transmission voltages are again stepped down to a lower voltage, that is now the secondary transmission, to a sub-transmission level voltage, maybe 66 kV, 33 kV, 11 kV and so on. So these sub-transmission level voltages are now taken into the substations, which are the primary distribution stations, where this voltage levels of 33 kV, 11 kV are directly used by the large industrial consumers, or they have to be again reduced to lower levels of 11 kV, 440 volts and so to be used by the small consumers, the households. And this 3-phase 440 volts enters into the colony end substation transformer, where each of the phases is fed individually to the households, catering to the load of the house. In this way, the 3 phases of the colony transformer is loaded uniformly with a certain number of houses, and thus here ends the consumption of the power that has been generated in the thermal power station. So we can see the beauty of the electrical power system, that power is generated in one corner of the world or the country, where it is transmitted to another corner of the country through the transmission lines. So the huge infrastructure that is used for the transmission and distribution system is commendable, and the maintenance of this transmission and distribution system is very, very tough job, which is being delivered very efficiently by our transmission line companies and the distribution companies of the various states, who always strive to keep the distribution losses to the minimum and increase the efficiency of the distribution lines, the transformers, the switchyard components and the system as a whole. So here we end our presentation on the generator, the working principle and its constructional features. If you have any doubts on any of the slides, components, you may please send your queries on my mail ID. Thank you for a wonderful session with you all. Thank you.